Hi, I'm happy to present our work on reactive synthesis for continuous robotic systems under uncertainty. Consider a robot with motion uncertainty tasked with going to a charging station. There is a wet area on the ground, and it has to dry off in the gray region if it traverses the wet area during execution. Another example is a search scenario in which a robot is tasked with finding a possible trapped human in each room, but there may be door blockages, and we don't know if the human is in any of these rooms. These problems have a task completion guarantee requirement under multiple possible events, but with no probability distributions. Existing works largely make one of three assumptions. The first is stochastic uncertainty. The problem is typically to compute expected or chance-constrained solutions with the condition that there is an underlying stochastic process. Another assumption is bounded continuous disturbance, which finds robust solutions, but is limited to relatively simple or continuous dynamics. Finally, a few works utilize a discrete transition system to synthesize a reactive controller, but these methods require a discrete or finite abstraction of the problem. The problems we consider may not have a known or underlying probability distribution, and the system may have complex hybrid dynamics. The task is one of reactive synthesis with reachability guarantees, and the combination of these aspects are not easily tackled by existing approaches. These problems can be modeled as non-deterministic hybrid systems, where there could be multiple possible transitions between modes, that is non-deterministic. These hybrid systems model problems with hybrid uncertain dynamics, discrete events with multiple possibilities, and logical constraints. A solution to this problem is a control strategy that guarantees reaching some goal set from an initial hybrid state. We tackle this problem as a minimax hybrid game, where the non-determinism is an adversarial player. Since directly analyzing the reachability of the non-deterministic hybrid system is undecidable, we instead search the game incrementally from the initial state. The game evolves in both continuous states and discrete modes, and starts at a starting state with the system player choosing from a continuous set of control inputs. Choosing a control propagates the continuous dynamics of the system. Then, the game transitions into the non-deterministic player's turns, which has a choice between a discrete set of actions. When the system hits a guard, the adversarial player may have multiple actions corresponding to the non-deterministic transitions of modes in the hybrid system. From there, each player takes a control or action sequentially until the goal state or termination condition is met. In the game tree, a strategy is a subtree formed from one action of the system player and all actions of the adversarial player. So, the game tree comprises of many strategy subtrees. A strategy is winning if all the leaf nodes of the strategy are in the goal. This game is an indefinite horizon reachability game with an infinite number of possibilities. So, a major challenge is how to effectively extend the game tree starting from the initial state such that we can find a winning strategy. Our work draws inspiration from two lines of research. On one hand, motion planning has shown to be very effective for exploration of a search space, but it is not very effective for searching for a winning strategy as it is difficult to tell which nodes to explore. On the other hand, Monte Carlo tree search effectively trades off between exploration and exploitation of trajectories, but does not efficiently explore the hybrid space since only one trajectory is sampled at each iteration. In this work, we propose sabers. It works by using a bandit-based strategy selection methodology to select a partial strategy in the tree for expansion. Then, a sampling-based motion planning algorithm is used to grow the selected strategy and hence search game tree. Then, the process repeats. This alternation of selecting promising strategies and expanding on them combines the exploration-exploitation properties of bandit-based techniques at the strategy level with the effectiveness of sampling-based motion planners. The heart of our framework is a strategy selection algorithm which optimally decides which strategy in the game tree to improve on. This is done by using the upper confidence bound equation with a min-max cost function that determines what percentage of the leaf nodes are part of a winning strategy. Starting from the root node, the algorithm selects a strategy subtree of the full game tree using this equation. This allows us to trade off between exploitation of the current best strategies with exploration of other strategies. The algorithm repeats until a winning solution is found. In our paper, we prove that our algorithm finds a winning strategy with probability 1 as iterations approach infinity. This is the first probabilistically complete algorithm for reachability of hybrid systems with nonlinear dynamics and discrete transition non-determinism. Now, Let's take a look at some results. First, we consider an autonomous car with non-deterministic transitions when attempting to switch gears, where it may accidentally switch to the wrong gear. Our benchmark results show that our method performs significantly better than RRT or MCTS alone, and is also at least 10 times faster to find solutions than an existing approach that performs a heuristic search method. Next, we consider the robotic charging system with uncertain motion, where the circles represent the bounded uncertainty of the robot. The robot is tasked with going to the green region and drying off in the gray carpet if it traverses the wet area. On the left, we see that the algorithm finds a solution that directly goes to the green charging station if the environment allows it, to guarantee that it will not traverse the blue region. But when the environment is more cluttered like on the right, the algorithm finds a conditional reactive plan that reacts to whether or not it traverses the wet area. Finally, we show a robotic search and rescue example. The task is to find possible trapped humans in a room, but the doors may be blocked. All unblocked doors should be searched before going to the exit region. Our algorithm finds a plan that reacts to these non-determinisms. In this example, the robot goes towards room A and finds out that the room is blocked, and decides to go to room B. The algorithm is able to react to the door status since it has a winning strategy that accounts for all of such variations. Now, the algorithm senses that room B is unblocked and decides to go into room B and finds the humans and completes the task. To conclude, in this work we propose the first probabilistically complete algorithm for non-deterministic hybrid systems with reachability objectives that avoids constructing a finite abstraction. Thank you.